Assalamu alaikum everyone. Welcome to today's video where we will be starting off the part where we will discuss about finding all roots. Now, the main difference between this part and the previous parts are quite simple and obvious. In previous part, we have even used an example where we have seen that an equation where the curvature was something like this, and you can easily find out that we either found one solution, this one or this one, but actually the system had total of two solutions. But the codes we have seen, the algorithms we have run, it can either figure out any one of these roots. So those algorithms actually fail to find all the possible roots, and thus this comes our next topic, which is finding all roots, not just a single root but all possible roots. In order to find all possible roots, we do not need to learn a completely new algorithm. In fact, we will first see to modify some parts of the bisection method to make it possible, so that this function is enough to find all the possible solutions. So as you can see over here, I have actually written the apply bisection method on x1 and x2. So over here the whole bisection method algorithm will go in this part. So we have already studied in details this part. The rest of the part, yes, that's new. So what will we have is we will choose lower limit a and upper limit b that covers all possible roots. When we are working in the bisection method, we only need to ensure that the initial two guesses x1 and x2 had the root within it, but now it has changed. Now we want to first choose a and b, two limits that covers all possible roots. All the roots are within that range, and then we decide on the increment size, which is del x, which should be very small. So then we set x1 equals to a and x2 equals to x1 plus del x, and while x2 is less than b, we apply bisection method on x1 and x2. Then we will move. Okay, so what does this algorithm do is, let's try to take a closer look over here. I think I should do it over here instead. What I'm trying to say, let's consider if the problem function is same as the before one. Okay, I think I should change the paint color. Let's say this is the axis and this is the function. Okay, now what we want to say is that we want to take very high limits. Suppose this is a, and we want to take this one, suppose this is b, and we can see that all the limits within this part is actually covered. Sorry, all the roots within of the function are covered within this part. So now what we will do is we will take 2 points. One will be over here and it will start with a. We will call it, suppose over here we say that we will set x1 equals to a, so we will say that this one is x1, and you can see that x2 will be x1 plus del x. So you will say, suppose this point over here is actually x2, and then we will learn what will we do, we will enter the while loop, which is x2 is less than b. Clearly it is true because x2 is over here and b is over here, and apply the bisection method, and we can already see there is no root. So what will happen after this, we will say there is no root, and after this is completed, what we did is we set x1 to be x2. Okay, so what have we done, we said that this x1 does not exist anymore, it will be cut off, and this x2 will be renamed as x1, it will be cut off, and the new x2 will be the small increment of x1. That means once again we will move over here, and the value will be will become x2, and again the same stuff happens. We will apply bisection, it will again fail, and then we will take a small step. This will become the new x1 and this will be the new x2, and this type of small movement over here. So when we get to this part, we will get one solution, and after that once again the values will keep on incrementing and we will go for small updates, and when we reach this limit we will find another root using the bisection method, and then we will move on until we have found the B point. When x2 is found to be less than when x2 becomes equals to B, then this loop will break, and thus we will cover all the possible roots. And this is how the modification of the bisection method actually helps us get the value of all the possible roots. Now there is one concept that we should remember is the importance of del x. Okay, so we have used del x as a medium to traverse the overall points. Now what happens if del x is too large or when del x is too small? Well, you see, if del x is too large over here, you can say that probably one guess was here. Suppose that this is the x1 and the new x2 is actually, and now if I say that x2 equals to x1 plus del x. Now if del x is way too large, then x2 will be over here, and you can see we have already skipped the two roots, and the condition will actually fail to see that there is actually a root within this range. So when del x is too large, the overall working principle it will fail. Now what happens when del x is too small? When del x is too small, over here you can see there are so many parts to check on, and it will actually evidently will make the system very costly. There will be a lot of operations, it will take longer time. So we actually need to decide on an optimal del x, but there is no specific rule to decide what is the perfect value of del x for a situation. It varies from one case to another. Usually this type of problems is also generally seen in mathematical places, like, and these are usually used in gradients solving problems, but usually in exam the value of del x will be provided, it will not be given to you to work with, so no big deal. But please understand that the value of del x has very high importance when it comes to getting our job done. Okay, now here comes the Newton's method, and there are some modifications of the Newton's method will actually help us. Newton-Raphson method will actually helps us to find all the possible roots as well. Okay, so in Newton's method, what we first need to do is record the number of root m, that is find the number of roots that are possible, which are n, and decide on some initial estimate or initial guess, which is x0. Now we have stored the number of roots in n, and while we find that not all roots have not been found yet, what we will do is we will find the root xr, that is xr will be the root, using Newton-Raphson method. Using Newton-Raphson method we will find a root xr. We already have the initial guess x0, we will use it and then deflate the equation. This is a very important step which we will need to discuss. Deflate the equation using xr. What is xr? Xr is a solution to the equation. So we will need to deflate the equation using found xr, and then we will set x0, which was the initial guess, to be the xr, and we will say the value of n can be decreased by 1 because we actually already have found one root. Okay, now the important topic of deflating the equation. I really need you guys to take some time and understand it and pause the video whenever needed. Every polynomial equation more or less can be expressed by equations like this. Okay, x minus 2 into x plus 3 into x plus 1 equals to 0. More or less every polynomial equation can be expressed like this, and yeah, we can actually calculate it, and we will find another equation which will be something like x cube minus something something something, so which will be equal to 0. For now we are not considering about this, we want this one. Now this equation over here, what will happen if I divide this equation by x minus 2? We can easily say that in that case, in this equation, this part and this part we cut each other out, and we will be left with only x plus 3 and x plus 1, right? Now if we rewrite this part, we will actually get an x square plus something equation, right? Now look carefully, this is a third degree polynomial equation and this is a second degree polynomial equation. So can we say that if we, now what will happen if we divide this x cube function by x minus 2 instead? Won't we get this function? If we do get this function, we will get this function. We can say that if we divide a function with a found root, then we can have the new equation with power reduced by 1. So once again, take your time, this is a complex topic. What is happening on, what is going on, you should take some time in pausing video, rewinding it again, trying to understand what's going on, and we will move on to the forward. But this part of dividing an equation with one of its roots and turning into a new equation, we call this step deflating the equation. We deflate, one is inflating and another is deflating, so we are reducing the equation. Why we are reducing the power it has. So this is the deflating equation part, and once the deflation is done, you can see that we in the initial function we used x minus 2 and x plus 3 and x plus 1, 3 parts. But when we deflated the equation, after the deflation, the new function did not contain the x minus 2 part because we divided the function with that part. So this root was reduced and only these two roots remain. So we do not need the this root anymore, and thus we can move on to the next part of this. Now we can move on to the remaining part of this algorithm. Now comes the deflation and synthetic division part. So deflation is the mechanism of reducing the power, and we achieve deflation by doing a synthetic division. In the previous slide, I have shown you a division operation that actually helped us to achieve our goal, but we cannot do something like that because we cannot divide x square plus 2x plus 3 divided by x minus 2. It will not work much in a mathematical equation. So this in a coding equation, so this type of operation is needed. We will not go very much into understanding the derivation of this part. What we should know is that the main equation is provided as px and the new deflated equation should be provided as qx. And we can say if xr is one of the root, what I am trying to say is one again, if I provide the previous slide, I am trying to say that we are given a situation like this. Equals to, once again, is actually the same, x minus 2 into x plus 3 into x plus 1, and in this line what we are trying to say that this is actually p of x is equal to, this part will be x minus xr, that is xr is a root of the equation, and the remaining part will be called qx. Okay, now we are expressing px using the coefficients of a, and we are expressing qs using coefficients of b. After that, there are some mathematical intuitions going on here which will not be a part of our course because it's mostly mathematical problem solving also, and then we will be left with this parts of the equation, and we will use this to update the values, to change the values, and so on and so forth. So this is actually the deflation part. Now I know this will, well, overall seems too much, and this is actually the end of our chapter. We will not continue anything today on, but I will request everyone to once again go through the videos, and in our class features actually we will actually try to work and provide some examples in all the parts we have done, and we will practice those examples, we will work on it, because throughout the slide we only covered theoretical topics, theoretical contents. We do need to do some mathematical practices, and so we will do some math practices as well after this video. So next class will be based on fully based on mathematical practices. So within that time, take your time and clear up your theoretical confusions, and if there are any questions, reach out to me. We will try solving those questions, we will try solving those queries as well. And after that, in next class it will be only on practicing maths, nothing else, because we have completed a whole chapter over here. So thank you everyone, today's video ends here. Hopefully we will have another session very soon. Assalamu alaikum.